In this video, we're going to look at some ways to prove trigonometric identities. So first off, a trigonometric identity is just an equation involving trig functions that is always true. So an identity is just an equation that is true regardless of what value we put in for theta or x or whatever our independent variable is. One of the things we're going to be doing in this unit is proving trigonometric identities. In other words, use things we already know to show that some of these equations are always true regardless of what value of theta we put in. So here I've given two examples of trigonometric identities, and I'm going to talk about some methods we can use to actually prove these, to verify they're correct. And the main tools that we'll have are the identities that we already know about sine, cosine, tangent, secant, cosecant, and cotangent. So we have our reciprocal identities, we have our Pythagorean identities, we have our quotient identities, we have our cofunction identities, we have our even and odd properties. So we have some things that we already know about these trig functions. We also have some things we know from algebra. We know how to factor polynomials. We know how to add fractions. We know how to break up fractions. We know how to multiply by conjugates to rationalize denominators. So we have some tools that we can use outside of trig that will allow us to solve some of these equations. So let's start out with the identity cosine theta, tangent theta, cosecant theta equals 1. So we're multiplying these three expressions, and I claim that this is always equal to 1 as long as all three of these things exist. So the first tool that we can use when we're presented with a trig identity that maybe we don't know how to start is to turn everything into sines and cosines. Okay, because we have our reciprocal identities and our quotient identities, that allows us to turn any trig function we want into sines and cosines. And generally, when we try to prove a trig identity, what we'll do is start with the left-hand side, or start with the more complicated side, it's usually the left-hand side, and try to simplify it to make it look like the right-hand side. So essentially, this is a process of simplification. So we're going to start with the left-hand side, and I'm going to rewrite it using just sines and cosines. Okay, so cosine theta is, of course, cosine theta. We multiply that by tangent theta. Well, tangent theta is sine theta over cosine theta. So there we're using a quotient identity. And then cosecant theta is 1 over sine theta. So there we're using a reciprocal identity. And now we just cancel. So we have cosine over cosine, sine over sine. Everything cancels out, so this is indeed equal to 1. Okay, so now let's take a look at this second example. So here we have cosecant theta over sine theta minus cosecant of negative theta times secant of negative theta equals cotangent squared theta. Okay, so here we have a couple more things that we need to do. And whenever we have a trig function squared somewhere in our identity, that's a good indication that we're going to have to use a Pythagorean identity somewhere. So we want to keep that in mind and note which Pythagorean identity we'd want to use to get cotangent squared. Okay, so to do this problem, again, I'm going to start with the left-hand side, and I'm not going to mess with this first expression yet. I'm going to keep it like so. What I'm going to do instead is to take a look at this cosecant minus theta and secant minus theta. Cosine minus theta, secant minus theta. Note that we have some trig expressions with theta in it. We have some trig expressions with minus theta in it. What we want is just trig expressions with theta in it. So to start out, excuse me, we're going to get rid of the minus signs that are multiplying the thetas. And we can do this using the even property of the cosine and the even property of the secant. So remember that secant is the reciprocal of cosine, so since cosine is even, so is secant. So we can rewrite this as cosine theta times secant theta. Because cosine negative theta is cosine theta, secant negative theta is secant theta. because these two expressions are both even. Okay, now I'll write everything using sines and cosines. So cosecant is 1 over sine theta. We're dividing that by sine theta. It's just the same thing as multiplying by 1 over sine theta. And then we have cosine theta times 1 over cosine theta is secant theta. Okay, so we have 1 over sine squared theta minus 1. Okay, and now again we want to think in terms of Pythagorean identities, and the Pythagorean identity that involves cotangent squared also involves cosecant squared. So what we're going to do now is to sort of do the reverse of what we were doing before, because again we want to try to work towards the Pythagorean identity involving cosecant squared and cotangent squared. So now we're going to write 1 over sine squared theta as cosecant squared theta. Okay, so now we have cosecant squared theta minus 1, and that's going to be equal to cotangent squared theta. All right, so to review, what we did first was use the even property of cosine and secant to get rid of the minus thetas. That's always a good place to start when you have a negative x or a negative theta or a negative whatever our angle is. Wrote everything in terms of sine and cosine next. Okay, and then we just simplified here. Did cosine over cosine is 1. 1 over sine times 1 over sine is 1 over sine squared. And then we did two things on the bottom row. The first thing we did was used a reciprocal identity to rewrite 1 over sine squared as cosecant squared. And then finally, look at that drip there, we used Pythagorean identity. Okay, so that is one track we can use to prove some trigonometric identities. Okay, so this is something that is pretty trigonometric. We're just using some of our fundamental identities. And again, writing things in terms of sine and cosine is a very powerful tool. If you're stuck on proving a trig identity, a lot of times just writing everything as sines and cosines will get you pretty far. Okay, the last example I want to work through in this video involves something a little bit more algebraic. Okay, so sometimes to start out we have something that can be factored, and if we pull out a greatest common factor, or if we factor something that looks like a difference of squares or a perfect square binomial, we can do some simplification from there. So next, let's take a look at the example secant x plus tan squared x secant x equals secant cubed x. And so again, the presence of this tangent squared tells us that probably we're going to be using a Pythagorean identity, and it'll be the one involving secant squared and tangent squared. So that's always good to keep in mind. So we note, again, looking at the left-hand side, secant x plus tan squared x times secant x both terms have a common factor of secant x. Okay, so what we can do here is pull it out. Okay, and rewrite this as secant x times 1 plus tangent squared x. Okay, so this is going to be using just some factoring. Now we have a 1 plus tangent squared x. Now we can use Pythagorean identity and the fact that 1 plus tangent squared x is secant squared x. And then finally, secant x times secant squared x is secant cubed x. Okay, and that's exactly what we set out to prove. We wanted to prove that the left-hand side was always equal to the right-hand side, and here we managed to do it. So this is one way we can use factoring. Another way where we don't use any trig identities at all, and I'll do an example of this in a later video, we may have a quotient where we can factor the numerator and then actually use one of the factors to cancel the denominators. That's something that is purely an algebra problem. We don't have to use any trig at all. So we'll look at that in a future video. We'll also look at things we can do if we have fractions. We can break up fractions, we can add and subtract fractions, we can change fractions by multiplying by conjugates.